A phase diagram is just a graph, if you will, that shows the three states of matter. And all phase diagrams look something like a Y, all right? And the Y, which I've kind of drawn right there, the solid is always on the left. The liquid is in the middle of the Y, and the gas is on the right side. So you can see that on that graph axis, you have pressure on the left, temperature on the right, and there's some really interesting kind of parts here. But why this is neat for scientists is that it can tell you things like what temperature a solid will go to a liquid, or how can I get my solid compound to turn directly into a gas. So there's lots of little kind of neat things about these phase diagrams, and we'll see some examples of them coming up. All of the phase diagrams look something like this one right here. This is the phase diagram for water. You can look in your textbook for an even better version stuff, but this one will work fine as well. The lines on there, the Y part are the lines. They show all the conditions at temperature and pressure where an equilibrium exists between the different phases. So these lines, the parts of the Y, will show you like when things boil and when things melt and sublime and all this kind of stuff. And you can also see what phase your substance will be in if you know the temperature and pressure. So these can be super useful for scientists and engineers and a whole bunch of different kinds of fields. This is a little animation that shows the solid, all right? Solids, again, are very rigidly held together, but there is a little bit of movement. It's not totally dead. The only time you wouldn't have any interactions would be at 0 Kelvin. So solids, again, pretty tight. Now, if you heat up the solid a little bit, i.e. go left to right on the graph, you get to the point where you have both the solid and the liquid. And this is where the process of melting occurs. So the purple dots on the right would be like the liquid version, and the more blue dots on the left would be the solid version. And at the melting point, you have both solid and liquid at the same time. If you keep heating up the substance, eventually all this stuff will turn liquid. We'll look at that in a little bit. But for right now, let's look at this graph down here. This is a phase diagram for oxygen, O2, all right? And one thing that's really interesting is in the picture we saw earlier for water, all right? The solid-liquid interface, which is this part right here, for water had a negative slope. And in this picture here, the solid-liquid line has a positive slope. Now remember, if the line goes up and to the left, it's negative, or in the liquid oxygen one with the graph right there, the line is going up and to the right, that would be a positive slope. If you have a positive slope, the solid phase is more dense than the liquid phase. And like we talked about earlier, if you have something more dense, it goes to the bottom, less dense on top. So what this means for oxygen here is with a positive slope, solid oxygen would sink in liquid oxygen. On the other hand, if you go back to the beginning of this question, which I probably should have started about, I get kind of excited here, water has a negative slope. It increases up and to the left. And if that's the case, the liquid phase is more dense than the solid phase. So remember, ice cubes in water float, which is really wild. Most substances are going to be like oxygen, they sink. But because water has a negative slope for that solid liquid line, it means that the ice is actually less dense. So for oxygen, which is again the graph there on the right-hand side, because there's a solid slope right there, it's like the solid is pushing down on the liquid. That's what works for me. The solid phase is more dense than the liquid phase, and most substances have this kind of phenomena. Water is one of the few substances, not the only one, but one of the few, with a negative slope, and that just means that the liquid phase pushing down on the solid phase, liquid phase is more dense than the solid phase. So again, this is just reiterating how next time you put an ice cube in liquid water and it floats, that's kind of a cool thing in my world. Okay, moving back to the phase diagram, heating up from the solid-liquid interface, and there you can see the negative slope for water, by the way, you get to all liquid. And liquids are held together, but the intermolecular forces are not as tough as they were for the solids. So there's more like flexibility, if you will. But if you heat that up even more, you get to the next point, which is where the liquid and the gas are both in equilibrium with each other. So there you've got the kind of purplish dots on the top representing the liquid, and the gas, the red kind of crazy looking dots on the bottom, that would be the gas. So at first it is an equilibrium. You have both liquid and gas at the same time. The liquids don't just instantly turn into gas. All right, it's kind of a slow process. You have to go through all the different speeds of the molecules to get them right there. Kind of cool. And then finally, you heat it up enough and all of your liquid turns into a gas. Everything goes crazy. So that kind of stuff is pretty simple. We see it for water. You can take the solid ice and turn it into a gas by heating it up. That part's not too bad. But you can also have a solid go directly to a gas. And for water, this is weird. We'll talk about that in a little bit. Some substances do this naturally at room temperature and pressure. Carbon dioxide is a good example, which is dry ice. If you've ever been to like a Halloween party, and sometimes there's like punch and it's kind of got this gas stuff coming out. The gas is actually carbon dioxide. Carbon dioxide goes directly from solid CO2 to a gaseous CO2. So depending on the type of substance, you'll see this phenomena more easily than not. But even water will do this, which is really strange. There's another point which is absolutely worth talking about, and that's at the junction of the solid, liquid, and gas lines, like the middle part of the Y. And they call that the triple point. And at the triple point, all three phases are in equilibrium. And this is kind of like science fiction mind-blowing a little bit, maybe to some of you, but you literally will have the solid phase, the liquid phase, and the gas phase all at the same time. And you have to have very specific temperatures and pressures to make this happen. I'll show you in a video here in a little bit. But again, in theory, in addition to all substances in theory being able to go from solid to gas directly, you also have a triple point for all substances as well. So again, this is the phase diagram for oxygen, and I want you to give me the name of the point, which is where pressure is 2 millimeters of mercury. And this isn't the world's best graph, but the 2 millimeters mercury is right there. And the temperature is this 54.34 Kelvin. So i.e., what is the name of that point? And like we just talked about, when the three phases come together at the crux of the Y, that's the triple point. All right, so that would be where the triple point is for oxygen. And again, all substances in theory have a triple point somewhere if you get to the right pressure and temperature. These show the normal boiling points, the normal freezing points, and the triple point for water. Now, the normal boiling point is where the water boils under 1 atmosphere of pressure, 760 millimeters of mercury. And obviously, that's 100 degrees Celsius. In Fahrenheit, it would be 212, but don't say that around me. I hate that. Anyway, long story short. Freezing point, 0 degrees Celsius, 32 Fahrenheit, or 760 millimeters of mercury. So if you want to get to the triple point of water, and there's a picture of it right there, you have to be almost at 0 degrees Celsius, which isn't too hard. The pressure has to be pretty small, though, only 4.58 millimeters of mercury. So that's not a pressure that most of the time is seen for water, but if you get there, then you have that cool little picture right there. This is a video showing cyclohexane at the triple point. And cyclohexane, its triple point, occurs at 6.33 degrees Celsius and 40 torr. And a torr in a millimeter of mercury is the same thing, so about 40 millimeters of mercury. But you see there it's turning into a solid, but a liquid is forming, so that would be like a normal boiling. And now it's starting to turn into a gas, but now it's turning into a solid. Oops, there's some liquid bubbling out, and there's the gas. So you can see how it's going back and forth. There's the liquid. It really can't make up its mind. There's liquid going to gas. I can sit and watch this for a long time. It's so cool. Again, all substances should have a triple point. You may have to play with the temperature and the pressure a little bit to get there, but it is kind of cool.